to check whether these three given vectors span R cubed or R3, we just need to show that these three vectors could become a linear combination of a certain, let's say, B vector. Okay? B vector, since we are on R3, you have B sub 1, B sub 2, and B sub 3. Okay? And that when we say that the three vectors is a linear combination of B vector here, this would mean we are also going to look for possibility for the value of k sub 1, k sub 2, and k sub 3 to exist. They are all scalars in such a way that here B sub 1, B sub 2, B sub 3 is equal to k sub 1 V sub 1, okay, plus k sub 2 V sub 2 plus k sub 3 V sub 3. So let's substitute the values for vectors v sub 1, v sub 2, and v sub 3, and this will still be as it is. B sub 1, b sub 2, b sub 3 is equal to k sub 1 of 2, 2, 2 plus k sub 2, 0, 0, 3 plus k sub 3, 0, 1, and 1. So this is still b sub 1, b sub 2, b sub 3 is equal to scalar multiplication 2k sub 1, 2k sub 1, 2k sub 1 plus 0, 0, and 3k sub 2 plus 0, k sub 3, k sub 3. So vector addition, this will b sub 1, b sub 2, b sub 3. I have 2k sub 1 plus 0 plus 0, so I still have that. Then 2k sub 1 plus 0 plus k sub 3. And I have 2k sub 1 plus 3, k sub 2 plus k sub 3. Alright? Then I'm going to have, since they are equal vectors, I could say that 2k sub 1 is b sub 1, 2k sub 1 plus k sub 3 is b sub 2, and 2k sub 1 plus 3k sub 2 plus k sub 3 is equal to b sub 3. Now we have this system of linear equations. However, we don't have exact value as mentioned to our b vector, b sub, which comprises of b sub 1, b sub 2, and b sub 3, because we just need to come up with a linear combination of the three vectors that will result to this b vector, and will identify if k sub 1, k sub 2, and k sub 3 exist. But then again, we cannot really show here the value for k sub 1, k sub 2, and k sub 3. But we can represent this in terms of augmented matrix. So you have 2, 0, 0, and then your b sub 1. 2, you have 0, 1, b sub 2, 2, 3, 1, and b sub 3. Notice that we still have b sub 1, b sub 2, and b sub 3 because we don't have their exact value here. Now, if we're going to look at this again, we cannot use here the Gauss-Jordan elimination. We usually do it to look for the values of k sub 1, k sub 2, and k sub 3. What we're going to do here is, instead of this augmented matrix, let's just have the coefficient matrix. Okay, this is the coefficient matrix. We have 2, 0, 0, 2, 0, 1, and 2, 3, 1. And according to theorem 2.3.8, we can actually establish that for a linear system of AX is equal to B is consistent. When you say consistent, there exists either exactly one solution or infinitely many solution, but it's also being clarified by theorem 2.3.8 that aside from ax is equal to b is consistent, we only have exactly one solution if and only if the determinant is, or let's say that's matrix A, is not equal to 0. So here we are not going to bother ourselves solving for b nor the values of k. Once we can establish that the determinant of this coefficient matrix is not equal to 0, it automatically tells us, according to theorem 2.3.8, that this system in the form of ax plus b, which is this one here, this ax, this is equal to b, is consistent and has exactly one solution. And if we are going to accept that according to here, that if the determinant is not equal to 0 and it has exactly one solution, this would mean that a certain value for k sub 1, k sub 2, and k sub 3 exists, which tells us that the b vector here is a linear combination of v sub 1, v sub 2, and v sub 3. Hence, it will fit the idea that these three vectors span R3. So that's the only thing we need to consider here. So if we're going to solve for determinant, we have plenty of process here. We can use determinant by cofactor expansion or the usual process. Let's have this determinant here. Again, I'm just calling this matrix A is equal to the product of 2 times 1 times 0 times 1, 0, plus this here 0 times 1 times 2, 0, 0 times 2 times 3, 0, minus, we have the motion from upper right to lower left, 0 times 0 times 0 is 0. We have 0 times 2 times 1 is also 0, but we have the value here, 1 times 3 times 2 is 6. We have 0 minus 6. The determinant for this coefficient matrix is 6, and this is not equal to 0. Then, according to theorem 2.3.8, this system of ax equal to b is consistent and has exactly one solution. With that, this means there is certain value for k sub 1, k sub 2, k sub 3 to exist, which tells us that b, vector b, is a linear combination of v sub 1, v sub 2, and v sub 3. And hence, we have v sub 1, or these vectors v sub 2 and v sub 3 span R3. So again, when we trying to solve or trying to show that whether the vectors span R3, we need to show that the vectors is a linear combination of a vector b in this form, b sub 1, b sub 2, b sub 3, because it's R3. And since we came up with this system here, to which we don't know the value of k's and the b's, we use the coefficient matrix and theorem 2.3.8 to determine whether it's not the theorem that it's determinant, but we're going to use the determinant, and then with the help of 2.3.8 to show whether it has exactly one solution. It only happens if determinant is not equal to 0, and with that we can now say that the vector b is a linear combination of v sub 1, v sub 2, and v sub 3, and hence the mentioned vectors span R3. Thank you very much for watching.